Hi everyone, in this video we are going to discuss about the unit quantities, performance characteristics of the turbine and specific speed of the turbine. So first we'll start our discussion with the performance of turbine under the unit quantities. The unit quantities are mainly used to predict the behavior of the turbine or performance of the turbine. In this case, we have to consider the unit head. The turbine is working under a unit head. The unit quantities are speed, power and discharge. If the power, speed and discharge we are considering under a 1 meter head, then it is called as unit speed or unit power and unit discharge. These three together are called unit quantities. One is unit speed, second one is unit power, third one is unit discharge. So the unit quantities gives the speed, discharge and the power of a particular turbine under a head of 1 meter, assuming the same efficiency. Unit quantities are used to predict the performance of the turbine. Coming to the first one, the unit speed. It is the speed of the turbine when the turbine is working under a unit head. It is noted with capital N suffix U, which is equal to N by square root of H. Coming to the second one, unit power. It is a power developed by a turbine working under a unit head. So here the formula for second and third one are interchanged. Please make a change. For the formula for second one is there in the third one. Pu is equal to P by H to the power of 3 by 2. Coming to the unit discharge, the discharge of the turbine working under a unit head, it is denoted with capital Q suffix U and the formula is Q by square root of H. These formulas are very important while solving the problems. You must remember the formula. So Nu is equal to N by square root of H, Pu is equal to P by H to the power of 3 by 2 and Q is equal to Q by square root of H. These three are called unit quantities. Unit speed, unit discharge and unit power is a definite characteristics of a turbine. If for a given turbine under heads H1, H2, H3, the corresponding speeds are N1, N2, N3, the corresponding discharges are Q1, Q2, Q3 and the power develops are P1, P2, P3, then here they are comparing the three turbines. They have taken three turbines and they are comparing the unit quantities between those three. First one, unit speed, Nu is equal to N1 by square root of H1. That N1 by square root of H1 is the unit quantity of a turbine number 1. N2 by square root of H2 is the unit quantity of a turbine 2. N3 by square root of H3 is unit quantity of turbine 3. For unit speed, Mu is equal to N1 by square root of H1, which is equal to N2 by square root of H2 is equal to N3 by square root of H3. This is possible only when it is having these three turbines having the same efficiency. Similarly, unit discharge Qu is equal to Q1 by square root of H1, which is equal to Q2 by square root of H2, Q3 by square root of H3. Here also it is same. Three turbines they have considered. When these three are having the same efficiency, then Qu is equal to same for all the three turbines. Coming to the unit power, Pu is equal to P by H into square root of H1, or you can write it as P1 by H1 to the power of 3 by 2. Both are same. So Pu is equal to P1 by H to the power H1 to the power of 3 by 2, P2 by H2 to the power of 3 by 2, which is equal to P3 by H to the power of 3 by 2. If speed, discharge and power developed by a turbine under a certain head are known, the corresponding quantities for any other head can be determined. So if you know, that means if you know Q1, H1, H2 values, then you can find out the Q2 value. Or if you know N1, N2, H2, then you can find out H1. Similarly, like that, you can find out any value if you know the three values. If you take any equation, N1 by square root of H1 is equal to N2 by square root of H2. If you consider that one, then you need to find out the one value which is not there or which is not given. That can be find out easily from this relationship. N1 by square root of H1 is equal to N2 by square root of H2. N1, H1 and N2 values are known. H2 value is to be determined. Then you have to use the relation N1 by square root of H1 is equal to n2 by square root of h2. Similarly, you have to use other equations for finding out the power or head or discharge or speed depending upon the problem. Please remember the formula. Next, coming to the specific speed of the turbine, the specific speed of the pump already we have discussed in the centrifugal pumps. What is the definition of the specific speed of the turbine is? The specific speed of a turbine is the speed at which the turbine will run when developing unit power under a unit head. This is the type of characteristic of the turbine. So, in case of centrifugal pumps, we have seen that is when the speed of the pump which is working under unit discharge and unit head, whereas in case of turbine it is unit power and unit head, because the output in case of turbines is power, whereas in case of pumps the output is Q. That's why in under root in case of centrifugal pumps you got Q, whereas in case of turbines you are getting P. Don't confuse with the equation because it looks same. Both the equations looks the same, but the specific speed of the turbine and specific speed of the pumps are different. You must remember n into square root of P is applicable in case of turbine and into square root of Q, because in case of turbine hydraulic efficiency is converted into mechanical efficiency. Mechanical efficiency is in the form of output power. That's why you are getting n into square root of P. P is nothing but output power, H is head, n is speed. Whereas in case of centrifugal pumps, that is n into square root of Q, that Q is discharge. In case of centrifugal pumps, mechanical efficiency is converted into hydraulic efficiency. That output is hydraulic efficiency. That's why we are using discharge in case of pumps, whereas in case of turbines we are using pumps. This expression is very important. For this, by using this equation you can tell whether the turbine is a pulse turbine or reaction turbine, Pelton wheel or Kaplan turbine or Francis turbine. In the first lecture I have given some ranges for specific speed. If specific speed lies between some values, that is comes under Pelton wheel, that range we have given. In short answer questions they may ask you the ns identify the type of turbine by giving the data related to speed, power and head value. Then you need to find out the ns value. Then this ns value you have to check with the table I have given in the first video, the specific speed range. Based on the specific speed range, then it should be go with, if it is 10 to 30, then that is comes under impulse turbine, like that. If it is having 20, that is comes under impulse turbine. Ranges we have given in the first table. Just to go through that one and remember this formula. Those two are very important, and these type of questions are very important in competitive examinations point of view and the external examination as well as internal examination point of view. Please go through it, the very important formula. Next, these are some of the problems. We will discuss this one in the next video. Point here they have given first problem. If you go to the first problem, they have given suggest a suitable type of turbine to develop 7000 kilowatts power under a head of 20 meters while operating at 220 rpm. What are the considerations for your suggestions? See, they have given power value as 7000 kilowatts and head value as 20 meters and speed value n is equal to 220 rpm. You need to suggest a suitable type of turbine and why you are suggesting the turbine. That is the question. See, in this all the values they have given, speed value, power value, h value they have given. Then find out ns value. For this ns value I have given a table. From the table you can suggest the suitable type of turbine. These two are same. These two are similar type of problems. Second problem is related to unit quantities. A turbine is to operate under a head of 25 meters. Head they have given, speed they have given, Q value they have given. The efficiency is 0.9%. Determine the power generated, speed of the turbine. This comes under unit quantities. That's all. Coming to the characteristic curves of the turbine. Characteristic curves of the turbine means these curves represents the performance, means how it is varying with different conditions. The performance is varying with the different conditions. Okay, if you look at this, these are the curves which are characteristics of a particular turbine, which helps in studying the performance of the turbine under various conditions. Various conditions means sometimes we will operate the turbine under full load, partial load, half load, like that. And speed also we will vary. Generally we will vary head and speed. At different heads or different speeds we will operate the turbine. So that's what under various conditions they have given the performance of the turbine under the various conditions is useful. Okay, these curves pertain to any turbine are supplied by its manufacturers based on the actual test. Here we have three types of characteristic curves. One is constant head curves or main characteristic curves, constant speed curves or operating characteristic curves, constant efficiency curves or mushkil curves. The name itself in first three cases or in the three curves represents constant head, means head remains constant. We will keep head remains constant and we will vary the other factors like speed, discharge and power, that is unit quantities. We will vary or we will study the performance of Nu, Pu and Qu under constant head value. Constant speed curves are operating characteristic curves. These are the curves while performing the experimentation. In our lab we have done the performance test on turbine. That curves represents the operating characteristic curves. That is, we are maintaining the constant speed. Under constant speed, how the head is varying and how the efficiency is varying, like that we have to discuss. On the constant efficiency curve, under constant efficiency, how the specific speed, unit power, unit discharge and unit head are varying. We have to discuss those three. So coming to the first one, constant head curves are main characteristic curves. Constant head curves means maintaining a constant head, the speed of the turbine is varied by admitting different rate of flow. Rate of flow is nothing but discharge. By admitting different rates of flow, by adjusting the percentage of gate opening, that is full opening or partial opening, 1/4 or 3/4 gate opening. The power P developed is measured mechanically. From each test, the unit power Pu, the unit speed Nu, the unit discharge Qu and the overall efficiency are determined. So the characteristic curves drawn under main characteristic curves are unit discharge versus unit speed, unit power versus unit speed, overall efficiency versus unit speed. So these are the curves related to the main characteristic curves of a Pelton turbine. Here they have written N is constant. That N is constant means speed is constant. Under speed constant, we have drawn the graph between Nu and eta naught. Nu is unit speed and eta naught is overall efficiency. Qe is discharge and Pu is unit power. So 25% GO means 25% gate opening, 50% gate opening, 75% gate opening, 100% gate opening. So efficiency always should start from 0. That's why all the curves has begun from this point. So 0 to the values. If you look at the diagram, at 75% gate opening, we are getting the maximum efficiency value. At 75% gate opening, they are getting the maximum value. At 25% gate opening, we are getting the minimum value for overall efficiency. Coming to the discharge will be obviously more. Discharge will be obviously more when the gate opening is full. That's why you are getting Qu value is constant or slightly decreasing for 100% gate opening, for 75% gate opening, for 50% gate opening and 25% gate opening. It is almost same. Qe is almost same with the variation of, as and speed is constant, discharge is constant. 25% gate opening or 50% gate opening or 75% gate opening or 100% gate opening. The discharge will be more when 100% gate opening. Discharge is less when 25% gate opening. Coming to the power, here power also starting from 0, because if the output power is 0, when output power value is 0, that's why it is starting from this value. Here the curve will start from 0. 100% gate opening, again 75%, 50% and 25% gate opening. The maximum power can be obtained at 100% gate opening. Next, coming to the constant speed curves or operating characteristic curves. In this case, tests are conducted at constant speed, varying the head and suitably adjusting the discharge. The power developed is measured mechanically. The overall efficiency is aimed at the maximum value. They have drawn the graphs between power and discharge, overall efficiency and discharge, overall efficiency into unit power, maximum overall efficiency and percentage of full load. There is no question of speed here because it is constant speed curve. In this case, the speed is varying, that's why they have taken on x-axis. With the variation of speed, this is performance main characteristic curves of the turbine. See, this nu is how overall efficiency is varying with nu, how qu is varying with nu, how pu is varying with nu. This is constant head, that's why there is no question of h value here. Sorry for the mistake here, not n is constant, this is h is constant, head is constant, not n is constant. Please remember that point, not n is constant. Coming to this one, constant speed, that's why in this question they have given in x-axis variables are q, p and percentage of full load, and these turbine is working under unit speed, n is constant. Q versus power and overall efficiency. Output power values increasing with the discharge, similarly overall efficiency is also increasing. P and eta naught, power versus overall efficiency. Power and overall efficiency will always start from 0, so that's why the curve is starting from 0. Whereas percentage of full load, 25% gate opening, 30% gate opening, like that. The percentage at 100% gate opening, the overall efficiency curve is like this. Percentage of full load means load we are having, we will apply load on the turbine based on the speed which the turbine is rotating, and the deflection will also comes from in our experiment we have seen that applying load on the turbine. Next one is constant efficiency curves. These curves are plotted from data which can be obtained from the constant head and constant speed curves. The object of obtaining this curve is to determine the zone of constant efficiency so that we can always run the turbine with maximum efficiency. That is the importance, very very important. This is a combination of performance characteristic curves and main characteristic curves and constant speed curves, and these are useful in determining the constant efficiency zone where you will get the maximum efficiency. Here they have drawn graph between speed and power for full gate opening. These are the curves. Here you got the speed value maximum. The speed value you got maximum at this p, at this power.